applications of differentiation. So the first topic that I would like to work on is something called critical numbers. So that's our first, the starting point. So we know how to differentiate. We're going to use now what we know from chapter 1 and move on to chapter 2 and talk about a lot of important applications of differentiation. I'm just moving my keyboard away from here. Okay, so the first topic, 2.1 is using first derivatives to max min. So we need the preliminaries. So we're going to talk here in general about max min. In other words, when a function has a maximum or a minimum or any number of, so max min. So the first topic is critical number. What is a critical number? Well, a function has a critical number in one of the two possible situations or both. So a function has a critical number or has critical numbers if, number one, f prime of x is 0. And of course, if this has solutions, of course. And number two, if f prime of x is undefined, comma, where f of x is defined. So a function has a critical number if this equation has solutions. It may not have. If it doesn't have solutions, then the function doesn't have critical numbers. And both can happen at the same time for a function. If the derivative is undefined at a particular value of x where the function exists or is defined. Okay, so I'm going to choose a first example, and then I'll let you choose, like always, anything you want. So here's an example, g of x, and then I have my where is it? The multimedia library is ready up here. Yeah, I have it. So I'm going to open it in a second, or here it is. So if you would like, I'll tell you which page to go to. So here's my shared screen. You can also already go to 201. 201. Okay? And we'll come back and choose from there in a minute. So I have a function, and the function is 1 plus 6x plus 3x squared. Can anyone identify the type of function? Can anyone tell us what function this is? What type?
A polynomial.
Thank you very much. It is polynomial. Very good. So do you think that its derivative will ever be undefined for a polynomial function? Let's determine it. Can anyone give us g prime?
6x plus 6.
Yes, so very good, wonderful. We started from in the correct order, indeed. 6x plus 6. Will this be ever undefined? No, it's not possible. A polynomial function is always defined and always continuous and always differentiable. So in this particular case, for this function, no critical numbers will come from f prime being undefined. So I'm checking now. I have to check for all functions. I have to check both. But the second one I don't have to, because f prime is always defined. Okay, now I have to check the second one. Can g prime of x be 0? Okay, I don't know, but I'm just going to write the equation. What type of equation is this?
Linear.
Thank you very much. So I move 6 to the other side, and I get -1. So this function has one critical number. And the critical number is obtained from the function prime set equal to 0. Only from the first source. Okay, and then I'll let you choose in a minute. But now the question is, why do I look for critical numbers? Why? So here's the answer. Only critical numbers can turn into max-min or not. So what I'm saying is a function has max-min only if it has critical numbers. And even then, it's not guaranteed. But if a function does not have critical numbers, it cannot have max or min. Again, if it has critical numbers, they may change into max-min, no guarantee. But if it doesn't have critical numbers, it's a guarantee that it does not have max-min. Okay? Okay, max-min, my page 2. Max-min are called also points of extrema. Singular extremum. Okay, so if we talk about max-min, we can also talk about points of extrema. Same thing. Finding max-min for a function or finding the points of extrema is the same thing. So I'm going to share now, so we can choose anything you want from this page. So let me move this further a little bit. Okay, so find any relative extrema. They are called relative or absolute. I'm going to write that down for you in a second. List each extremum along with x value and at which it occurs, then sketch a graph of the function. We're not going to sketch the graph of the function. We are not prepared to sketch graphs right now, other than for quadratic or linear. We are going to be able to graph this by the end of this chapter in great detail. So I'm going to skip this. There is no need to do it right now. We're talking about something else. Okay, so can anyone choose? Anything from 1 through 34.
Well, how many do you have to copy?
So,
19.
which one?
19.
19, you said?
Correct.
Okay, perfect. Let me copy it. So this is 19 on 201, and it's f of x 1/3 x cubed minus 2x squared plus 4x minus 1. I'm checking. 1/3. Yes, x cubed minus 2x squared. Yes, plus 4x minus 1. Yep. Okay. Very good.
I believe it's negative 1/3.
Let me take a look. Thank you so much. So, did I copy something?
Oh no, I'm looking. No, never mind.
I always want to check. Okay. Even if you're wrong, I'd rather go back and check, because sometimes I copy a little piece from. Remember, my computer is like 3 feet away from me because of all the devices are on my table, right, between the computer. So I'd rather go back and check. Thank you. Okay, so before we continue with this, I just want to explain what they meant, or what it means, relative and absolute. Okay. So I was going to explain it anyway. So let's suppose we have a function, and we notice that this is a maximum, and of course this is a minimum. And in this particular case, this, let's say the function starts here and stops here. This is our example. So this is the maximum where, remember, the horizontal line The tangent is horizontal, which means the slope is 0 at that point. Same thing here. Slope is 0 at that point, as we discussed a long time ago. And we can show that the function exists on both sides of this tiny interval, and all function values are smaller on both sides than this value. That's why this is called either a relative or local max. It doesn't matter how you want to call it. Either you call it relative or local, it's the same thing. Because this function starts here and ends here, this point is also an absolute or global max. There is no need for both. Let's go with relative so I don't confuse you. Let's go with absolute. It doesn't matter. They are the same thing. They mean the same thing. Also, this one is a local or relative because, again, I can show the open interval where function values are bigger than this particular one. The slope still 0, of course. It's a local minimum. But it's also an absolute minimum because there is no other value lower than it. Here, there is no other value higher than it. That's why it's a maximum. These endpoints can never be local or relative. Why? Because I cannot show the open interval on both sides. So this could only be a global, either minimum or maximum. But in this case, there is a value higher than it and there is a value lower than it. That this is nothing. But it can never be local. Never. An endpoint is local. Never. Local or relative. Same thing here. I cannot show the open interval. Okay, so coming back to our problem, we're asked to find if the function has any points of extrema, relative or local. We'll see if we graph it, and we'll see whether it has an absolute or global, but I don't want to really graph these functions. We're going to have plenty of time to graph them in a lot of detail in this chapter, with a lot of detail. So at this point, I have to determine the critical numbers. Because if this function does not have critical numbers, then I'm done. I will say no points of extrema. Finished. So I have to find critical numbers. I know that critical numbers come from two sources. I have to check both. The first one is that f prime of x is 0, and the other one is f prime of x is undefined. Again, we selected a polynomial. This is not possible in this case. There is no polynomial whose derivative is undefined. So I have to find the derivative, set it equal to 0. Why? Because I'm looking for the points where the function has a horizontal tangent. They can be max or min, and we'll discuss which one in a minute. Good, so let's find f prime. Can anyone give us f prime for this function? Anyone who said nothing so far, like, I don't know, Zukra or Tyler?
X squared minus 4x plus 4.
Very good. So x squared minus 4x plus 4. Awesome. Thank you very much. Good. So now if you remember the first day of classes, you will tell me what this is, what this factors into.
A minus b squared.
Excellent. X minus 2, everything squared. Perfect. So now when I set it equal to 0, what do I get for x?
Would it be two numbers? Would it be 2 and
Correct, but they are the same.
Oh, that's right.
Exactly. There will be two solutions when I set this equal to 0, but both are the same. So this is a critical number. Now the question is it a max, min, or none of the above. A critical number does not have the obligation to turn into a max or a min. So now we're going to go back to our favorite table. That's why I insisted and insisted and insisted. And I will continue to insist. This time we will have f prime of x as the first row and f of x as the second row. The domain of this function, I know you're going to say negative infinity to infinity because it's a polynomial. X equals 2 will be in the table, and 0 for the first derivative. The first derivative is 0 when x is 2. First derivative is 0 when x is 2. Then we are trying to identify whether this is a max or a min or none of the above. I will have to plug in 2 in the original function. Why? Because I need this number here, this value for f of x or f of 2. Okay? So I'm going to share my screen. So let's do this. Where is my, okay, here it is, in y equals. So clear everything you have. Let's enter this function. And I have in parentheses, please, 1 divided by 3. Close the parenthesis. Then we have x cubed. And then minus 2x squared. And then plus 4x. And then minus 1. And go to second and table when you're finished with that. And please plug in 2. Go to the right and see that this is 1.667. Okay, so 1.667. I put it in. Here's our next step. Don't do anything here. I just want to come back to a graph that we talked about so far.